All right, group 1. Which subatomic particle would you like to come up with? Yeah, that's the easy one. So how many protons? 17. It's the bottom left-hand corner. Periodic table says so. It has to be 17 protons. So we'll go with 17 P for protons with a positive charge. Cool. Group 2. Which particle would you like to address?
Neutrons.
Neutrons. How many neutrons? 18. How'd you get that?
35 minus 17.
Right. It has a total mass of 35. We know protons are big, so that's a mass of 17. Subtract, you should get 18 neutrons. Questions, how we got that? Group 3, how many electrons? Yep, and how'd you know that? Which means we have an extra negative, correct? So we have 17 positives. You have to have 18 negatives, giving you an overall -1 charge. Quick show of fingers. How many of those 3 numbers did we get right? Okay, Holly, a question. Yeah. Generally in chemistry, we don't write the number 1, just like H2O. We don't say H2O1. So yeah, it's just understood to be a 1. Yep. That's the mass number. That's how heavy that nucleus is. And what's in the nucleus? Well, it's the protons plus the neutrons. Electrons are like little fleas. Yes, they have mass, but they're so light. You would need about 2,000 of them to equal 1 proton. Are there any elements on the periodic table that come close to 2,000 electrons? No, the most would be like 118. So, I mean, that's going to add a fraction of a proton's mass. We don't even really care about that. Questions on that? All right, group 4. What symbol are we going to write down for this next example? AG, yeah. How'd you know it was AG?
Because there's 47 protons.
Yeah, because 47 protons. Henry Moseley, each element has a unique number of protons. We're going to organize the periodic table that way. So you go to 47, that is AG or silver. All right, so then what other number do you want to come up with? Group 5, do you want to do the mass number or the charge? Mass number? Okay, what's the total mass of this isotope? What was it? Oh, how'd we get 93? Yeah, 108. You're going to add the 2 big particles together, the nucleus particles together. That should be 108. Top left. Questions on that? All right, and groups. The charge. It's going to be just a plus. I guess you could do 1 plus or +1, but yeah, plus is fine. Because we have 47 positives, we have 46 negatives. That gives us a positive in the top right corner. Good. Quick show of fingers. How many of those 4 numbers and letters did we get right? Okay. It seems like it went fairly well. Are there questions I can answer? Anybody know what other symbol we'd have to add up on the board here so that we get a holiday song? AU, which is what, 79? And we don't know exactly which isotope it is. We could go with, I don't know, 197 is probably close enough. Gold probably also, if it's an ion, is going to have a +1 charge. Put that together, you get what? Silver and gold. Questions? Maybe not my funniest way. Okay, so let's go ahead and take a look at our pre-lab from the front board here. A lot of them are just basic definitions, but are there specific definitions you would like some extra help with? So atomic number, Henry Moseley said that's the number of protons. That's going to be the bottom left number. That's what's on the periodic table. The mass number is the mass of the nucleus. That would be the protons plus the neutrons added together. That's how we identify isotopes. You could have carbon-14, carbon with a mass number of 14 in the top left. An isotope is a specific weighted version of an atom. So, for example, carbon 14 is different than carbon 12. Hydrogen 1, hydrogen 2, hydrogen 3 would all be isotopes of hydrogen. Atomic mass. Notice how these two words are different. This would be mass number. Atomic mass is what's printed up on the periodic table. And you'll notice that there's a lot of decimals up on the periodic table. Any ideas from your calculations why there's so many like decimal points up on the periodic table? Whereas mass number is a whole number. What's the difference? Quick conversation in your small group. All right, back as a whole group. Group 7, any ideas why mass number is a whole number, but yet atomic mass is all those decimal places? Sweet. All right. Cool. Group 7, thoughts? Jordan? Electrons included? Yeah, not really. When you add protons and neutrons together, would you agree you always have to get a whole number? You can't have like a fraction of a proton or a fraction of a neutron. But what did you do to get the atomic mass? Like if you take a look at what you did for calculation number 2, on the back side there, discussion question number 2. Did you get any decimal points there? Because atomic mass is an average mass. There's some math work involved. There's decimal points involved. So mass number is kind of a simplified whole number. It's the specific mass of an isotope. This atomic mass is a weighted average mass of these mass numbers. And because the percents can have decimal places, because it's an average, that's why we get decimal places. Any questions on why the percent sign tells us to divide by 100 and we always move the decimal place twice? Everyone comfortable with that? Sometimes people get messed up on really small percents. So, for example, when you say 5%, some people are like, I'm just going to move the decimal one place, and they get 0.5. 0.5 would be what percent? 50%. And really, really small percents, like let's say if this was 0.05%, some people are like, I'm not going to move the decimal place today. And they just say 0.05. Not the same thing. 0.05%, you'd have to move the decimal place twice and get 0.0005. So always move the decimal place twice. Why are a lot of people going to tell me at the end of this question number 7 that the average is 64? How do you know that 63 and 65 is going to give you an average of 64? What did you do to get 64? Oh, yeah? You add and divide by 2, right? Seems reasonable. From your math class, what's another way of writing divide by 2? Right? Yeah, multiplying by 1/2. Now, which one of these am I going to multiply by 1/2? One, both? Like, for example, do I multiply this one by 1/2 or do I multiply this one by 1/2? I like where you're going with this. I just want to make sure we're clear. Okay, so you have to add them first. So put that in parentheses. That's what you mean? Add them first and then multiply by 1/2? Sure, I like that. Good. If you have a number on the outside of parentheses, what could you do to those parentheses? Distribute? Yep, I like it. So we're going to take 1/2 times what? 63? Plus 1/2 times 65. We're still doing the same thing, right? Yeah. I'm not doing any like voodoo math up here. Okay. What's another way of writing 1/2? 0.5. I like where we're going with this. So you could say 0.5 times 63. And then you could say 0.5 times 65. Add those two pieces together. All right. See where we're going with this? What's another way of writing 0.5?
50%.
Ooh, 50%. So what you're really saying is I could take 50%, as long as I'm going to write that as a decimal, times 63, and 50% of the number 65. Now, if you don't believe me, chuck that in the calculator. Make sure you still get 64. You will, but I just want to make sure that you understand that. %50 of 63 would be what? 31.5? Half of 65 should be 32.5. Yeah, I think we get 64. It's just a different way about thinking of an average. So this is called a simple average, an arithmetic average. Okay, you add things up, divide by the number. In this case, it's 2. That's the same thing as saying 50% of my average is number 1, 50% of my average is number 2. In real life, is that always a fair assumption? That the two numbers are weighted equally? With grades, are they weighted equally? No. Tests are worth more. Quizzes are worth less. Homework's worth even less. In the lab, did you have the same number of every type of paper clip? So can I just say, well, half of them weighed 63 and half of them weighed 65? No. Real isotopes in real life, are they equally weighted? No. As long as these 2% add up to 100%, we can distribute them however we want. For grades in here, well, maybe we say it's 55% tests and 45% quizzes. That's fair. That's going to more heavily weight your average towards this number. Thomas, you doing all right over there? Seems a little dark over there. Looks a little shady. You want me to turn off the lights a little bit? Okay. We could say, well, let's really heavily weight this. 90%, 10%. It's supposed to be a joke, but that was even better than the first one. All right, 90%, 10%, fair enough. The average is going to be a lot closer to 65. And what if we really weight this heavily? 99%, 1%. You probably don't even have to do the math. The average is almost going to be equal to 65. It's like homework in here. The only way it really counts is it helps you on tests and quizzes, plus you get that 2% bonus at the end of marking period. That's weighted more heavily than if I even graded the homework. Getting a 2% bonus just for doing your homework, that really helps your grade out. Even more so than if I graded it at, like, let's say 5% and graded it for accuracy. You're probably not going to get every single homework question right at 100%. So the fact that you just do your homework and give you a 2% bonus, that really helps your grades out. Any questions about how a weighted average changes the weighting scale, the relative abundance in an average? So at the end of the activity yesterday, I had some people adding up the two pieces, and then they wanted to divide by 2. Why can't you divide by 2 at the end of a weighted average? Quick conversation in your small group.
There's nothing.
Back as a whole group, why can't we divide by 2 or divide by 3? Or if there's 5 pieces, divide by 5 at the end of a weighted average. That's not normally how we do averages. Normally we add and then we divide by 2 or 3 or 4 or 5. Why can't we divide at the end of a weighted average? Here we just add them up, divide by 2. Why don't we just divide by 2 at the end of doing this math? There's different amounts of each number. And how did we take that into account? what did we use to kind of take into account the fact that there's different amounts of each? The percentages. And would you agree multiplying by a percent is really doing the division at the very beginning? So if you're going to use a percent, that really is the division. So by using a percent, you did the division first, and then you're going to add the pieces together at the end. If you divide by 2 at the end, you doubly divide it. You can't do that. You're going to get the wrong answer. Does that make sense? Doubly divide. All right, so then if we go ahead and take a look at our data up here, I just want to make sure we're good to go on the lab calculations. Everyone got 29 paper clips? Good to go. Everyone got a pretty heavy paper clip for the large one, about 0.8, maybe 0.9. For the medium size, about 0.4-ish. Somewhere around there. And then the small one was not that much smaller, about 0.3. Everyone okay with coming up with an average mass for each paper clip? Okay. As far as abundance, would you agree you take the number of each paper clip divided by the 29? So we get about 17% the large paper clip, 31% the medium paper clip, 50% the small paper clip. The average will be closer to which one of those paper clips? Foster? It's going to be the small paper clip because half of our average is made up of these small paper clips. And the medium paper clip wasn't that much different than the small paper clip. Almost 80% of our average should be pretty small. So right now, I'm thinking the average should be pretty close to 0.4, the weighted average, because 80% of our average should be about 0.3 or 0.4. And sure enough, when you do math, and this is where some people got tripped up, the relative abundance, they accidentally forgot to put that in as a decimal. So if you get a 43-gram paper clip, you're like, man, that's a piece of a paper clip. I've seen paper clips that big. I mean, they're like this big. I use them on my trumpet music stand at home, just like at a wedding like this, so the paper's not blowing everywhere. So, I mean, they do sell paper clips this tall, but that's, we weren't anywhere close to that back in the day. Now, just to prove a point, if you had done a simple average, if you had simply just added these 3 numbers up and divided by 3, it's going to be more heavily weighted towards the 0.8. Adding those 3 numbers up, dividing by 3, would have given you a simple average of 0.519. Obviously, that's incorrect. We use a weighted average, which should be close to 0.43. So, would you agree the 2 parts needed for a weighted average would be the percent, also called the relative abundance, if you write it as a decimal, and the average mass, whether it's the mass of a paper clip or it's the mass of an element. All right, then down below here, I think I added this here. There's another way you could do this. Would you agree if you add up all the paper clips, you're going to get about a total mass of, let's say, 8, 9, 10, 11, about 12 grams? Correct. If you add up all the paper clips, like if you just pile all of them on the balance, you're going to get a mass of about 12.5 grams. And if we give each one of those paper clips a vote, if we weight each one of those paper clips equally, divide by 29, notice what you get. You get 0.431. Which is the weighted average, because we allowed each one of those paper clips to have a vote. If you simply just add up the 3 types of paper clips and divide by 3, that's basically assuming that you have the same number of each type of paper clip. You can't do that. It has to be a weighted average. Questions on that? So then we're going to apply that to elements down below. That's going to be our lesson for today. So basically our lesson today is just a review of exactly this. If you understood question 3, you're golden on today's lesson. So would you agree copper 63 has a mass of 63? Is it 50% of all the isotopes? No, it's about 69.15%, written as a decimal. Copper 65 weighs 65 atomic mass units. And from this graph here, that's about 30.85%. So we write 0.3085. You do the math, you're going to get 43.56 and 20.05. You add the 2 together. Are we going to divide by 2 at the end? No, because multiplying by the percents really incorporated that division by 2. We just decided to unequally weight it. Show of hands, you got 63.61 when you did it. 63.61. Okay. Quick conversation in your small group. I think we have about half the class on board here. Quick conversation, help each other out, make sure that we understand how to get to 63.61. We'll give you a minute to clear that up.
Looking at it now, I understand.
Yeah. What are those percent? These percents is out of all the copper isotopes, like out of all, like a penny, you have a penny, it's made of copper. 69% of those copper atoms weigh 63. 30% of those copper atoms weigh 65. You can't just add 63 and 65 divided by 2, because that would assume 50%, 50%. This mass spectrometer graph is actually where we get those percentages from. Those percentages are where we got these percentages. We'll talk about that in our slideshow today. Any questions how to get 63.61?
What is that represent?
So that's the portion of the average assigned to the 63 isotope. So if you take 69.15% of the number 63, this is the part of the average. So let me say it this way. Let's say that these are tests and quizzes. Okay? So if, let's say your test average in this class is a 63%. And let's say tests are worth almost 70% of your average. If you decide to blow off every single quiz and you just want to cut the quizzes out of your grade, you would end the marking period with a 43.56% because you're missing all of the points, all of your average from the quizzes. Now, obviously that doesn't happen. So then we take a look at, well, what's your quiz average? Your quiz average is 65%. That's worth 30% of your grade. So when you add that in, these are the two parts of your grade. How do I get your total grade in here? We add these two pieces back together at the end, and you would end up with a 63.61. Not the greatest grade, so you probably want to go back, do some vocab tests, some other things to get that grade up. But that's where your grade would be if those are your averages for each category, and those are the weight factors for each category. And again, we're not going to divide by 2 at the end because multiplying by a percent takes all that into account. Yep. All right, questions?
Did you get 0.6915 and 0.3 of? Oh.
The percents written as a decimal. You can't plug a percent into the calculator because percent means per century divided by 100. Now, if the question was, well, where did we get these numbers from? We put the copper element in a mass spectrometer, just like J.J. Thomson invented, and you're going to get a graph that looks like that. That's 69.15%. That's 30.85%. All right, group 1, you have a lab quiz on Monday. So what sort of new things would you incorporate, or what uncertainties do you have?
I know we should do is like actual element.
Oh, like real life elements?
Yeah.
Buy a mass spectrometer, put it in there, and like separate the elements based on. Sweet. So when you're rich and famous, you'll donate a mass spectrometer to my classroom so I can do that?
Yes.
How many years is it going to take for that to happen?
About 17 and a half.
All right, I got about 17 more years in me. Sweet. Let's do it. All right. Can I get that in writing?
Maybe later.
Okay, sweet. Number 2. Hey, I got an IR this year. That's $16,000. Why not shoot for $85,000? Let's get a GCMS in here. $85,000. $120,000. They're pretty amazing. All right, group 2, something new or uncertain.
We should have done like.
Oh, big old paper clips, yeah. That could be fun. One giant paper clip per group. That'd be cool. You find some, you get them, I'll add them in. I would need, what, eight big paper clips, ginormous paper clips, like Dollar Tree paper clips. It would probably be in the big eraser and the big pencil section. So, yeah. Okay, group 3, something new or uncertain.
Well, we said that you're still confused about calculating the average, but
Makes sense now? You take a percentage times a mass or whatever you're calculating. Group 4.
I split everything more like with weighted average.
Ooh, like actually calculate your grades by hand? That would be cool. Yeah, it's really not that hard, right? Tests are worth 55% of your grade. Quizzes are worth 45% of your grade. So if you know your test average, you simply multiply by 0.55. If you know your quiz average, multiply by 0.45. Add those two pieces together, that's what the computer does. Now you got to be a little bit careful with finding the category average. I do a doubly weighted average in here. So for example, some tests are like 35 questions. Some questions 40, some tests are 42 questions. To me, that seems a little bit unfair. I think Unit 1 is just as important as Unit 2. So what you would have to do is you would simply kind of average your percents. I plug every test in as 100%. So to do that, you can't just add up all your points in the category, divide by total points, because that would be a straight old average. I do a weighting factor on each category. So if you add up all your percents for a category, like we did at the end of the marking period, getting ready for family conferences, I had you do that. So that would give you your test average, multiply by 0.55, add up all your percents and average them in the quiz average, multiply by 0.45, you'd be good to go. Good. Group 5, something new or uncertain?
What is relative abundance?
Relative abundance. So this is a percent. This would be relative abundance. How are they related? It's basically the decimal form of a percent. Yeah. And again, you have to use the decimal form of a percent in a calculation. Group 6, something new or uncertain? You could use even smaller paper clips. Okay, that would be cool. Can you think of anything other than paper clips we could do? It's the same item, but there's different forms of that item. Oh, you could do like plastic paper clips. You guys are really like fixating on that paper clip idea.
You could do buttons.
Oh, you could do buttons, different size buttons. That could be kind of cool. Kind of shaped like a button. Jingles around in your pocket.
You're really tiny.
A tiny what?
Really tiny paper clip.
You guys are really fixated on that paper clip. Coins. You could say, I have the coinium atom. Are all coins massed the same amount? No, big atoms would be like quarters. Smaller versions or smaller isotopes could be the dimes and the pennies. Do all pennies weigh the same amount? No, if it's after 1982, it has a zinc middle to it. So it's going to weigh less. Before 1982, they were solid copper. That would be a heavier isotope. So you could do like an isotope penny lab. You could do an isotope coin lab. They're all coins, but they weigh different amounts. That's what an isotope is. Group 7, something new or uncertain. And don't say paperclip one more time.
Maybe we could use marbles because like marbles have a different.
Oh, different size marbles or ball bearings. Yeah, that could be cool. Yeah, I like it. Sweet. Any other thoughts? Lab quiz on Monday. Questions? All right, let's tuck that away. Let's get out slide 37. If it's okay with you, I'm going to skip this slide. Carbon 12 and 13. Most people are going to want to tell me the average is what? 12 and a half? Can you do that? No, that would just be a typical average. We can't do that because 98.93% of all carbon atoms weigh carbon 12. So the average has to be super close to 12. So would you agree you would have to take 0.9893 times 12 plus 0.0107 times 13? Chuck that in the calculator real quick, see what you get. The weighted average of carbon should be what? Probably just a smidge over 12. 0.9893 times 12, 0.0107 times 13. I get 11.87 plus 0.14. Add that together, I get about 12.01. If I'm talking about a single atom, obviously that's not going to be weighed in grams. That's called the atomic mass unit, or AMUs. Now, I could scale that up to an entire mole of carbon atoms, and then I could say you have 12.01 grams per mole. And the cool thing is that answer has decimal places. Mass 0, 1. Masses on the periodic table are weighted average of all those isotopes. Pretty cool. Questions on that? So again, carbon-12 is a specific mass number, a specific isotope. Carbon-13 is a specific isotope. It weighs 13. The atomic mass is a weighted average. That's why it has decimal points. How do we determine what those percentages are? You would need a mass spectrometer. This is how it works. You vaporize the sample. Now you have all these carbon atoms flying through this instrument, this tube here. Heavier ones are going to basically fly off the track. They're going to fly out towards the outside. It's like a tractor trailer going around the turn. It's going to feel that momentum more so. Whereas a lighter atom is going to go zipping around this curve at a smaller angle. So the cool thing is we can basically animate that or represent that. So again, it was J.J. Thomson that came up with this instrument because it's basically like a cathode ray tube. He put magnets on the outside. He put charged particles on the outside. So notice how as all of these carbon atoms are zipping around the turn here, the red ones take too wide of a turn and they get hit by this detector slit. They never make it and hit the detector. The blue ones go zipping around the turn and they go too narrow of a turn and they hit the detector slit. Only the green ones are perfectly tuned to be hitting the detector. So let's see what happens when I lower the magnetic field strength. I can measure this magnetic field strength. The red ones don't even make it around the turn. The green ones take too wide of a turn and now hit the detector slit. And it's only the blue carbon atoms that have the right energy to hit the detector. Again, I can measure that magnetic field. I can measure the voltages. I can come up with all these relative percentages, and let's turn up the really strong magnetic field. Notice how it really zips the blue one around the turn. It bumps into the corner of the turn, doesn't even make it around the turn. The green one takes too narrow of a turn and hits the detector, and now the big, bulky carbon red atom has just the right energy to hit the detector. This is exactly how a mass spectrometer works. So really what we often do is we pair this up with a gas chromatograph. Because we have to vaporize the sample, we have to turn it to a gas. The gas chromatogram that I showed you up here in the last lab, that's basically going to allow the samples to travel through at different rates. Different atoms will go through the gas chromatograph at different speeds. And then if we add the mass spec component onto it, we can identify what all of those samples were. And when we do that, we get a relative abundance of each one of those isotopes. We get a graph that looks like this. A bunch of the, well in this case copper, a bunch of the copper-63 ions hit the detector, and only a few of the copper-65 atoms hit it. So the red numbers up here would be the actual height of the peak. And then we simply have to turn that into a ratio. So 69.15% of copper atoms weigh 63, 30.85% weigh 65. I think that was Owen's question. Where did the percents come from? They came from this graph, which came from that instrument, which is a mass spectrometer. Questions on that? All right, so with that being said, your homework, and you have just a little bit of time, you might be able to knock this out, page 14, 1 through 5. Now, even though you're going to be using a calculator on this, can I give you credit for calculator work? No, so you're going to have to show kind of what you're typing into the calculator, put some answers down, and then your final answer. So these graphs are way too small to read. But again, I wanted in your back of your mind that these numbers are coming from a mass spec graph. Which if you sign up for AP Chemistry, Abigail even did like a whole little POGL activity, whole 2 lesson on a mass spectrometer. So if you're interested in that, sign up for AP Chemistry. What you guys are doing problem 1 through 5. Percentage as a decimal times mass. Percentage as a decimal times mass. Add the pieces together at the end. If you forget how to do that, there's a nice little solve for example at the top. Sweet, that's it. Happy Friday.